Okay. So, okay. Good morning, everyone. My name is Tina, and today I will be presenting my PhD project on human and biomechanical considerations in hand disease. So I'm 5 months into my PhD in the Faculty of Engineering and Physical Sciences. My project supervisors are Dr. Alex Dickinson, Dr. Cheryl Metcalf, Professor Marcus Heller, and Professor Martin Brown. I know that Mike mentioned that I would be talking about wrist disease, but in this case, I will just be talking about hand disease today. So it's important first if we start talking about hand osteoarthritis, also known as hand OA. Osteoarthritis is a degenerative joint disease that can occur in any of the joints in your body, including your hands. And it's characterized by the breakdown of cartilage, the changing of shape of the surrounding bone, and the thickening of the joint area. So we can see this on the image on the slide, which compares a healthy hand to an osteoarthritic hand. So if we look at the two, the blue area joint has more of a smooth cartilage, whereas the red area has it broken down, and it's the same with the bone. It's much more rough in the red area, and we can see also there's much more thickening in that place. In the hands, OA symptoms can vary, but they most commonly include joint pain, joint stiffness, difficulty in moving your fingers, a weakened grip strength, and also the swelling and tenderness around the knuckles, and that's what we can see here on the image. This can be described as a biomechanical problem because it affects the function, the motion, and the structure of the joint. So we've talked about how it can be a biomechanical problem, but it can also be a clinical problem. Arthritis Research UK said in 2013, more than 1.5 million people sought treatment. And the success rate of treatment for smaller joints, such as in the hand, does not match that of what we see in the larger joints, such as the hip or the knee. This indicates that there needs to be further development in our understanding of these smaller joints so that we can sort of catch up and close that performance gap between the smaller and larger joints. On the slide here, we have a Swanson implant, and that's a popular finger joint implant, so a type of treatment. It replaces the joint. But even though it has a high failure rate, it still remains the gold standard. So here again, we have that clinical problem. So we talked about how it's a biomechanical problem, a clinical problem, but it's also a human problem. Our hands are such an essential part of our everyday lives. We do so many things with them, from writing things down to communicating to even getting dressed in the morning. So for somebody living with hand OA, that can have a significant effect on an individual's quality of life. So of course, it changes how a person can do certain tasks, and their capabilities may be lost. So overall, we can say that hand OA presents a major socioeconomic problem and a barrier to healthy aging, whilst compromising a patient's daily life. We've sort of talked about how it can be categorized into 3 main areas, and research can be approached by considering any one of these areas. But as you've seen, it's not just a biomechanical or a clinical or a human problem, but it's a problem that lies within all 3. So that's sort of the motivation behind my project. It's trying to take a more holistic approach to trying to improve our understanding in hand OA. So that's why we've got this line. Can we talk about the biomechanical, clinical, and human aspects all together? So that's where we move on to talking about musculoskeletal modeling, so MSK modeling as well. I think it's important first to talk about what we mean about musculoskeletal. So the musculoskeletal system is an organ system that gives animals, including humans, the capability of movement. It also provides structure and support and stability. And here on the slide, there's an image that demonstrates the human musculoskeletal system. And it's made up of different elements. So we've got here the cartilage, the muscles, the bones, the tendons, and the ligaments. And it's these parts of the human body that become affected by disease, such as osteoarthritis. So the actual mechanisms responsible for providing human movement are very, very complex. And they're so complex that sometimes it can be difficult to measure them experimentally, even impossible. So that's where a tool such as MSK modeling can be really valuable. It's a non-invasive computer-based tool that can be used to study how the body works or the certain mechanics of biological systems. And what we mean by non-invasive is that it doesn't require any type of surgery or dissection of a participant. It just means that once you have your input data, you can do all your investigation on a computer. So it categorizes the bones, the joints, and the muscles, and simulates and tries to understand how they move and work together. So I talked about how my project was multidisciplinary. So in engineering and health sciences, which is sort of how my project crosses, they use MSK modeling to improve clinical assessment and as a tool to improve the design of certain treatment. So to actually generate an MSK model, you need a combination of different types of data. And the three main ones would be motion data, force data, and image data. So the image on the slide actually demonstrates how we can move from somebody walking in a lab to our MSK model. So here we have a person here, and they have attached to them various electrical measurement devices, but the most important one are these markers. And as the person moves, the position of these markers are recorded and then translated onto a computer to get what we have on the right-hand side, which is the model. So we've got force data as well, which I mentioned, and that's something important because it allows us to measure what external forces are happening as somebody is moving. And then the 3D image data is just a way that we can obtain this underlying structure of the skeleton. So that was taken from maybe CT, computer tomography, or MRI, magnetic resonance imaging. So what can we actually measure using MSK modeling? So here we've got a labeled MSK model of the human body, and it details all the different areas that you can investigate. I've talked about how it's a good way of recreating different aspects of human development, function, and disease. So a great thing we can measure is sort of how particularly does the human move. So what sort of ranges of motion is happening. Additionally, it can also be used to see what type of internal forces are happening as the joint moves. And again, we can also try and understand how the muscles and the soft tissue play a part in all of this. So I've given a little bit of basis on what MSK modeling is in general. So going back to the whole studying of hand disease, I think it's important to just mention that building a complete and accurate model of the human hand remains a challenge, and this is mainly because of two main factors. The hand has a very complex architecture. So as you can see on this slide already, it's made up of many different parts. So you have the tendons, the bones, the nerves, the arteries, the muscles, and all of these are essential for hand function, but they're also very difficult to simulate on a computer. So even the bones, in one hand, there's 27 bones, and they have such a small area, so that can also be difficult. The second factor that makes it difficult is that the hand has very complex movement. So firstly, our hand can range from doing really big movements, from clenching our fists, to really small movements like pinching. And again, the fingers can move independently to each other. And that again is something difficult that, simulating on a computer is hard. So I've talked about the difficulties of generating an MSK model of the hand, but there are some out there. And of course, there are limitations. And that's something we have to talk about, particularly because that's what we're trying to tackle with this project. On the slide, we have an image here that details a study that was taken in 2018 that was based on the validation of a hand exoskeleton. And in this study, they used MSK modeling. So we have a few of the elements that we've already discussed. So in picture A, it's those markers I was talking about. So you recall those markers' position and you try and understand how they change during movement. So B is sort of the mathematical representation of the positioning of the markers. So then we move on to C, and that's your generated MSK model on your computer software. And D is just how this particular study incorporated the exoskeleton. So I don't know if I mentioned, but these red lines on image C, those are the soft tissue. So it's the representation of soft tissue. Here I would say, and as you can see, A and C are very different. One of the main limitations is that there is an oversimplification of what is happening in the real world. So sometimes it's easier mathematically to make assumptions, but it doesn't actually represent what is happening in the real world system. So this can, limit the type of limit the validity of findings sometimes. So that's something that this project hopes to tackle, to see what kind of areas we can improve in accuracy. So one way we are hoping to enhance our MSK models is using patient and public involvement. And this is one way that we can specify our research and come up with a design brief that includes the knowledge of the end users. So of course, PPI is all about doing research with people rather than for them, and living without the condition. As researchers, we don't always know what's important. So PPI could be there to help us enhance and include what is important from a patient's perspective. For example, in literature, some things might be missing that they haven't considered, again, living without the condition. Is there certain criteria and certain things that the model should do that the patients find important in studying hand disease? These are all things that hopefully by involving patients and the public, we can find out. So I think it's important first to mention that last year, I was involved in an undergraduate group design project, which had the aim of designing a finger joint simulator. So this is a testing machine that would be capable of testing the success of a new implant for hand disease. So we were able to incorporate some PPI into the study, and we found it very, very valuable. And so much so that we were able to come up with certain testing criteria based on the discussions that we had with members of the local OA community. So these testing criteria ended up being that an implant should be able to provide joint stability, it should be able to improve endurance, and it should also be able to improve grip strength. So all of these three things were implemented into our joint simulator. And these are things that we may not have considered without going on to the PPI work. So this leads on to the current plans for this PhD. We aim to take more of a collaborative approach. So again, we were limited with time with the undergraduate group design project. So this time, with the years ahead, we hope to sort of expand on the pilot study, expand our PPI community, and try and find more of the criteria that have to do with hand disease that are based on the patient's perspective. So again, having this research being very patient-led. And as well as involving lots of patients, we also want to involve other project stakeholders that would have an effect on this type of research. So that's the clinicians, such as the surgeons and the occupational therapists, and also the GPs and the consultants, because at the end of the day, the main approach we hope to take is by including those three main elements that I discussed before. So the biomechanical, clinical, and human perspectives. So to summarize and also talk about the next steps, hand OA presents a major socioeconomic problem and a barrier to healthy aging, thus compromising a patient's daily life. MSK modeling is a tool that we hope to use to further our understanding in hand OA, and we also hope to consider all of the angles, so the biomechanical side, the clinical side, and the human side in hand disease, so that we can further enhance our MSK model. It's very important to say that building a complete and accurate MSK model of the hand remains a challenge, and its oversimplification is what makes it the most limiting. And overall, my main research question is how will incorporating the public's voice inform the design of the musculoskeletal hand models? So my next steps are to expand our PPI community, to contact the other project stakeholders, so our clinicians, our GPs, our consultants, and also to generate an initial finger model using existing data. So I've discussed that the end goal hopes to be an MSK model of the whole hand, but currently in the first year, we're hoping to start small and then work our way up to a whole hand. So here are my references, but overall, I just want to say thank you very, very much for listening. And if you have any questions, let me know.
Thank you, Tina. I'll stop recording.